and just give you some perspective for this assignment. The big picture for this assignment is that you are asked to get your own data from EMOS, and the key atmospheric observable that we're going to be working with is the air pressure. So you can see that down here. Let's have a look here. Maybe do that in some obnoxious color right here. Okay, and you'll notice that there are two values of pressure that are provided. The first one corresponds to the value actually recorded at the station. So this is the value recorded at EMOS itself, and it is 988.0 hectopascals. And what you're going to see is that next to it is a value that is higher and has this designation, the MSL pressure. So MSL stands for the mean sea level, and we are getting somehow from EMOS the mean sea level pressure equivalent. So just like we use UTC, Coordinated Universal Time, as our reference time base for observations that are going to make their way onto surface analyses, observations that are made by weather stations at the surface, we use mean sea level, 0 meters, as our reference elevation. So basically what this question is about is, really working on this transition here, figuring out how to correct pressures that are recorded at weather stations to mean sea level equivalent pressures. And you'd be wondering, well, why do you need to do that? The answer as to why you need to do it is right here. EMOS, the York University Weather Stations, is 196 meters above mean sea level, and so we need to account for that. And that's basically what we're trying to do in this particular exercise here for assignment 3. Okay, so again, if I just get my handy markup capability going here, this is the equation that we're going to be making use of. It's called the hydrostatic equation. You end up, the unknown is the mean sea level equivalent pressure. So this is the unknown. And we have various knowns. We know the height at which the observation was made. That's the 196 meters, so we know that. Little g is the acceleration due to gravity. We know that, and we will work with the density of the atmosphere, but essentially that's unknown for most of these questions. We'll actually dig into density a little bit more, as you'll see from some of the other questions. And then over here we have the observed pressure, which is something that is also available from EMOS. And that's this value right here. That's the observed pressure. Okay, so I'm going to go through the first question. Let's go back to here. So the first question asks you to obtain a screenshot for EMOS itself, right here, and also, and that's the figure that I was just showing you, and I'm going to go back to that in just a moment here, but also to obtain data from a weather service like the Weather Network or something comparable for a weather station that's close to EMOS. So you shouldn't find that to be too much of a challenge. So again, what you're trying to do here is obtain a screenshot that looks just like this. Now, obviously, you cannot use this one. This one was obtained on July the 13th, and so we'll know if you use it. But you should obtain your own screenshot. All right, and that's expected as part of the assignment. Okay. So let's go back. The first question, so that was question A. Obtain a screenshot similar to figure 1 and include it in your submission. Okay, so don't forget to included. That's important there, right? Included in your submission. Okay, so then we have to state from EMOS, state the height in meters above mean sea level of the station. So we're looking for the height. So we'll go back to our screenshot here. Forgive me for all this switching around. I'm still getting used to this thing. So this is something I did point out to you before, but it's right here. This is the 196 meters. So looks like for question B, all we have to do is state the height. So let's put that into our solutions over here. So for B, 196 meters, and that's the height of EMOS relative to SL, or mean sea level. Okay? Now we can start moving on and doing some of the more interesting stuff. So we're going to assume that the value for density is 1.2041 kilograms per meters cubed. Let's put that into our notes here. So density, 1.2041 kilograms per meters cubed. So that's a value of density. Density, as you can see, is defined in terms of a mass divided by a volume, and this is the standard value of density for the atmosphere. I'm not sure if I actually say that anywhere. Yes, here we go. So 1.2041 is the value for the density of air at STP. And STP stands for standard temperature and pressure, 20 degrees Celsius, and the average value for surface pressure of 1,013.25 hectopascals. Now, we already know, based on our EMOS data, that we're going to be looking at a value ultimately it's close to 1,013. It's not off by very much. It's only 1,011. So this value for at least pressure isn't going to be too far off. But our temperature, actually, coincidentally for this one, our temperature is also very close to the 20 degrees Celsius for STP. So this should probably not be too bad an estimate. Anyway, so let's go ahead and do the next part. So we've got our value for density, and then let's take our value for lift G, the acceleration due to gravity. And what else do we have here that we're given? And then we need to list down our P observed. So let me put down little g. Again, this is the acceleration due to gravity, 9.81 meters per second squared, and P observed, we're going to get that from our EMOS data, and so each of you is probably going to end up with a slightly different value here. That's for us by design, and the value that we're interested in here is the value at the station, which is our 988.0 hectopascal. Let's put that down as our P observed, 988.0 hectopascals. All right, let's see where we're at now. So as far as our equation goes, we have our density, we have our acceleration due to gravity. From the previous question, we have Z observed, and we also have our P observed. So let's looks like we're in good shape to make the pressure estimation. So P MSL is equal to P observed plus rho G Z observed. That's the equation that you've been given. Now all we're going to do is we're going to substitute in the various values. So P observed is 988.0 hectopascals plus density 1.2041 kilograms per meters cubed. Tell you what, let me put all of this on the next line just to make the break a little bit more convenient. So this is all part of the same calculation. Density 1.2041 kilograms per meters cubed times the acceleration due to gravity of 9.81 meters per second squared times the height of EMOS as far as the observation goes, 196 meters. Okay, so let's go ahead and carry this forward. You'll notice that I'm being quite meticulous to keep my units together here. You're going to see why momentarily. All right, so I found myself a calculator and I've entered in the numerical values. So again, just to remind you, 1.2041, that's of course our density of the atmosphere, STP. The 9.81, that's our acceleration due to gravity, that's a constant, and the 196 is of course the elevation of EMOS. So let's go ahead and do the arithmetic here, and we get 2,315.19 blah blah blah. Let's have a look here. Our smallest number of significant figures is 3. So really, you know, we are only really justified in keeping the 2,315 here. That's going to be enough in terms of significant figures. So 2315. And now things get interesting, because we've got all these funny looking units here. So let me just have a little bit of a side discussion with you about units. And maybe I'll even do this in a different color just so that it is very clear that this is a little bit of a side discussion. So we're trying to figure out the units that need to be attached to the 2315. From the density, you can see that we have kilograms per meter cubed. From the acceleration due to gravity, we have meters over seconds squared, and from the altitude, from the height of EMOS, we have meters. So let's collect all of this together. Looks like we have kilograms times, and then here in the numerator we have a meter times a meter, okay? And so that's going to give us a meter squared. And in the denominator we have a meters cubed and a seconds squared. Now, doing a little bit of handy-dandy cancellation here, we have meters squared in the numerator and meters cubed in the denominator, and if we do that cancellation, we'll end up with just meters in the denominator. And so these are, believe it or not, the units that we are left with, and that is a kilogram over a meter times a second squared. In the metric system, this is defined as a Pascal. Let's write that out. That's the name of a very famous mathematician and scientist, Blaise Pascal, philosopher, and the unit for pressure in the metric system, the Pascal, bears his name. Okay? All right. So, netted out then, if we go back to our calculation, and part of the reason for doing this is I expect you to be able to work through the units, but it's very important, and you're going to see why in just a moment here, because I'm going to make a huge point of how people make this most mistakes. So the units that are appropriate after the 2315 are pascals. Okay, now the astute viewer of this tutorial will notice that we have pascals here and hectopascals here. And in the metric system, we like to use hectopascals as our unit for pressure. So the next thing we have to do is we have to convert between pascals and hectopascals. Now the good news is that conversion was provided to you right here. Whoa, that's terrible. Let's try that again. Right here. In fact, so are the units. So let's just quickly do a quick recap on that. This is exactly what we got from our working with the unit there. So a pascal is equal to a kilogram divided by a meter times a second squared. Okay, that's what we just determined as well. And now we're going to use this conversion factor. 1 hectopascal is equivalent to 100 pascals. Let's put that into our book here. So 1 HPA is equal to, I used 3 symbols in the assignment. Two equal signs is just equal, 3 equal signs is equivalent. So I don't like this now. All right, let's try and make that a little neater. 100 pascals. All right, so basically what we now need to do, let's just go ahead and rewrite where we're at in our calculation for the mean sea level. We're just going to go ahead and rewrite what we have above. 988.0 HPA plus 2315 PA, and then we're going to multiply this second term here by there is 1 hectopascal for every 100 pascals, and that's just far too crammed here. Let's try and see if I can do a bit better. Got a little carried away with my use of space there. 2315 PAs. Let's do it like this. There is 1 hectopascal for every 100 pascals. Okay? Let's just check that we got that right again. Make sure we didn't make any mistakes. Right here. One hectopascal is equal to 100 pascals. So I think we're good. 1 hectopascal for 100 pascals. Okay, now you'll notice that very conveniently, in terms of units, and again, I'm a huge advocate of keeping your units because obviously your units help to guide you in terms of where you are. We have pascals here in the numerator. We have pascals here in the denominator, so the pascals are going to cancel out, and we're going to be left with hectopascals. All right, so let's carry this forward to the next line. .0 hectopascal. All right, we're almost finished with our calculation here. Let's keep the numerical values out front. 235 divided by 100, and the only units that are left over are the hectopascals. So basically we have 988.0 hectopascal plus, when you do the division here, you end up with 231. Let's see, that would move 2 decimal places, so it would be 23.15. We're really only justified here to 3 significant figures, so let's call it 23.2 hectopascals. And then we'll use our calculator. We can just use our calculation from before, divide it by 100. We get our, again, our 23 point, basically 2 when rounded. Add that to 988, and we get 1011.2 1011.2. So go ahead and write that in here. 1011.2 hectopascals. Okay, how did we do? Let's compare that with the value that EMOS has. And it looks like it is extremely close. EMOS provided its own conversion of 1011.3. This is a little bit unusual. You may not get such a close comparison. I think the reason why the calculation that I just did ended up being literally 0.1 hectopascals different, which is very small, is because, as I mentioned before, STP is almost applicable here. The 1011 is very close to 1013 standard pressure, and 19.6 is very close to 20 Celsius in terms of the standard temperature. So this result is actually very close to what you would expect. Before I move on here, I do want to just point out that right here, this is the biggest mistake that people make. They forget to make the conversion between hectopascals and pascals, and obviously you can see it's a huge implications here. So if you end up with a pressure in HPA, you think it's in HPA, and you're over, if you're over 1,000 and, I don't know, 1,060 or something like that, chances are you've made an error along the way. So it's extremely important to value your units. I kind of like to say units are your friends. Follow through, you know. You'll make fewer mistakes. So let's just see if we can finish off this question here. So where are we? Back here. So we're working on question C, and so all we're asked to do in this question is to calculate PMSL. And then in question D, we're asked to make the comparison. Compare and contrast the results of your calculation above with the EMOS reported value. So the EMOS reported value is 1011.3. Okay. So this is going to be question D. EMOS P MSL, or if you like, we can do it like this to put it all together. That kind of makes it extremely clear. 1011.3 hectopascals as compared with the value that we just derived above. Question 1C, we got a value right there, 1011.2 hectopascals. We can conclude, therefore, the 1C estimate is extremely close to the EMOS value. And again, this is not necessarily required, but the reason why the two values are so close is that for the date and time of observations, the STP, how are we going to say this? Maybe that conditions, yeah, for the date and time of observations, conditions we're very close to STP, standard temperature and pressure. And that's why we got such close values here. And again, don't be alarmed if, based upon you having different values to work with, you end up with values that aren't quite that close. That would be expected. This is unusual. Let's continue along with this calculation. We're now at question E. Question E. As you can see here, we assumed that there would be some difference between the estimate that you just made as well as the EMOS value shown here. In the example I happened to choose just randomly at 13:15 UTC on July the 13th of this year, I happened to pick something where the values were very close to UTC and the values really, really small. Anyway, we're going to go through the calculation because you're going to have to do this yourselves anyway. And what we're going to do is try and make a new and improved value for density. And the way that this works is we are going to use again the observed pressure from EMOS, which we have here, and we're also going to use the observed temperature from EMOS. We're going to use the air temperature that is shown right here, 19.6 Celsius at a 2-meter height. EMOS does also offer a ground temperature, but notice that this is actually at 5 centimeters worth of depth, so we're not going to touch that. We need to make use of a constant called R in this calculation, and so this is the calculation that we're going to go through. As you can see here, this equation derives from something called the ideal gas law, which I believe at the very least I alluded to in the lecture material. The ideal gas law is a classical law that came to us via chemistry. It's been around for well over 100 years at this point, and it is an approximation. It's an approximation in which the atmosphere is assumed to be a so-called ideal gas. In other words, its properties vary in various simplified ways. Now, it turns out that assumption of the assumption of an ideal gas applies actually quite well to the atmosphere in general, and so it's convenient to make use of it. So we're going to go ahead and do the calculation based on equation 2 here. So it's rho observed. This is now part E. Rho observed is equal to P observed. That's the observed pressure divided by some constant that we have yet to elaborate on, and the observed temperature. Okay, so P observed again is our 1,000, oops, hang on a second. No, it isn't. P observed is in fact the this value here, the 988 hectopascals. .0 hectopascals divided by R, and R is a constant which is valued at 287. Where is it here? Here's the value of R. 287.058. 287.058 joules divided by kilograms times kelvins. That's a bit of a mouthful, isn't it? So R is the constant that applies in the case of the ideal gas law. That's what I'm trying to say. Now, T observed. T observed, let's write it in here because we're going to make a little conversion. T observed is equal to 19.6 degrees Celsius. But you'll notice that there's this appearance of a capital K here. And that K is a unit for temperature. It's Kelvin. And so to convert this value in Celsius to Kelvin. And the way to make that conversion, if we now say T observed here in Kelvin, 19.6 degrees C, plus the conversion to take a temperature in degrees Celsius and convert it to Kelvin is you have to add 273.15. So basically, let's go ahead and do that. Take our calculator again. 19.6 plus 273.15. All right, so we're making the conversion to Kelvin. 19.6 Celsius plus the conversion factor of 273.15 gives us 292.75. 292.75 Kelvin. 292.75. Now, in this calculation, we have four significant figures from. Well, we only have three significant figures from our EMOS observable of 19.6. So really, if we're true to significant figures, then we have a temperature here of 293 Kelvin. That's really as much as we're really justified to use here. So let's go ahead and put our 293 into our equation right here. 293 Kelvin. Okay, and now we'll go ahead and do the arithmetic here. All right, so what we're going to do now is we're going to plug all of these numbers into a calculator and go ahead and do the arithmetic. So we'll start off with 988.0. Where's my calculator? Let's start on a clean slate. So 988.0 divided by, now we've got two numbers, we need to multiply those numbers, so we're going to use brackets. And the first number is the ideal gas constant R, 287.058. 287.058, that looks good. And then multiplied by our temperature that we converted, which is conveniently shown to us here, right here. And we said that that was 293. And we'll close the bracket. And now we're ready to go ahead and do this arithmetic. Something clearly went wrong. And here's what went wrong. I could have said I meant to do that, but I didn't. The problem is right here. And again, it's our units. The units that I left this in were hectopascals, but the equation assumes pascals. Okay, so what we're going to do is we're going to rewrite this. We're going to rewrite out, oh geez, I just realized I made another mistake here too. This should have been rho observed here. So carrying along, rho observed is equal to 988.0 hectopascals times 100 pascals for every hectopascal divided by, this is the beauty of having a digital setup here, is I can erase things. So 988.0 hectopascals times 100 pascals per hectopascal divided by, and there's no change in the denominator, 287,058 joules over kilograms times kelvins times 273 Kelvin. Okay, now going back to our calculator, the only thing that we really messed up was the numerical value here. So maybe take this as another best practice to be careful with this as well. So if we go back to our calculator mode, and let me see if I can actually, looks like I can edit what I put in before. So when I multiply out when I do this multiplication, of course, what I'm going to get, I guess I should have really written that out, shouldn't I? Let's try it here. So I'm going to get 98800 pascals divided by 287,058 joules, kilograms, kelvins, times 273. So nothing in the denominator has changed, and we've just increased the numerator by a factor of 100. All right, let's do that arithmetic. So here we are back over here. We'll add in the 2 zeros. So now it's, whereas before it was just 988 hectopascals, now it is 98,800 pascals. And if we do the calculation, we get a value much more along the lines of what was expected. And again, just to be clear, what we're calculating here is, of course, the density. So it's 1.175, which is even stretching the significant digits a little bit, but we can go ahead and do that. So density observed, 1.17, what do we say? 1.175 to that many figures, 1.175. Okay. And I'll do the units in just a second here. All right, now we just have to work through the units. A little bit messy, but it's worth going through here. Again, you don't have to know how to do the conversions. Let's just recall that a pascal here is equal to a kilogram divided by a meter times seconds squared. So a pascal is equal to a kilogram times a meter times seconds squared. Okay, so we have pascals in the numerator. Actually, let's take it a little bit of a step at a time. Pascals in the numerator, joules divided by kilograms times kelvins in the denominator, and then there's another K from the temperature value. So these K's cancel, and you end up with pascals in the numerator divided by a joule per kilogram. Now there's a elementary, what was it? An elementary result, let me leave it at that, as a bit of a loss for words, regarding fractions. When you have a fraction divided by a fraction, what you do is you invert and multiply. So basically, this manipulation with units transforms into pascals times kilograms per joule. And now we're going to start expanding things. One other thing that I'll mention to you here is, and I guess I might as well mention it down here, joule is a unit of energy, again named after a very famous scientist. A joule is equal to a Newton meter, force times a distance, and it just so turns out that a Newton is a kilogram times meters per second squared times another meter here, so a joule turns out to be kilograms meters squared divided by seconds squared. Okay, so this is a little bit messy on the units front, but again, I'm just showing all of this to you so that you can see that it actually does all work out. Okay, so actually maybe what we'll do is we'll just go ahead and simplify the second term here with the kilogram or a joule. So kilograms, actually, sorry, let's do it like this. Kilogram divided by joule is equal to kilogram, and then the joule we just found out is a kilogram meters squared over a second squared. So again, we can simplify this by inverting and multiplying. So the kilogram from the numerator is multiplied by, when you invert, seconds squared ends up in the numerator, and kilograms meters squared ends up in the denominator. The 2 kilograms cancel here, one in the numerator, one in the denominator, and as you can see, we end up with seconds squared divided by meters squared. Okay, so now we can go back to multiplying that by a Pascal. So now we're actually working towards the units for density. So we have a Pascal times seconds squared divided by meters squared. And we know from what we did previously, we just reminded ourselves, our definition for a Pascal is right here. Definition for a Pascal is that it is a kilogram divided by meters per second squared. A kilogram. So the Pascal, kilogram divided by meters times seconds squared. And then we're going to go ahead and bring down the result of making our division of what was it? Kilograms divided by joules up here. Bring that down. That was just seconds squared divided by meters. Now we can start to simplify things. So in the numerator, we have first kilograms. Now if you look at the time units, we have a second squared in the denominator and a second squared in the numerator. So those both cancel out. And then the only other thing we have to account for are the meters. We have a meters times a meters squared. So meters times meters squared is meters cubed. And remarkably, we end up with the right unit here. These are density units. So kilograms divided by meters cubed. Mass divided by volume. So all of this was to say that the value we ended up with right here, and again, you're not expected to go through the units conversion that I just went through, but obviously it does help to understand it. So what we ended up with here was a value for the observed density of 1.175 kilograms per meters cubed, and that is in fact the answer that you were looking for question E. Right here, calculate density. So we did that. Now what we have to do is we have to go back. So sorry, since let's see, do I actually have it here? Oh, I guess I already. Anyway, we just did the density calculation. And now what we have to do is recalculate the mean sea level equivalent pressure based on our new and improved value for density. All right. Let's go back to here. So this is now, I think, question F. So P MSL via improved density, which was rho observed. So again, the idea here is that the reason for doing this is to really account for the actual temperature and pressure as opposed to the assumption of STP. So now we're going to go ahead and do that familiar calculation. We need our P observed. It's the same as before. Let's grab it from EMOS. It's the 988.0 hectopascals. Our density is now the observed density based on the calculation that we just did, and it's right here, 1.175. 1.175 kilograms per meter cubed. Little g, the acceleration due to gravity, is the same as it was before, 9.81 meters per second squared, and our height of observation is of course also the same. It's our 196 meters here. So we'll just restate the hydrostatic equation. The mean sea level equivalent pressure is equal to the observed, let's get that right, the observed pressure plus rho, now rho observed, times little g times the height at which the observation was made, the altitude loss. So we'll go ahead and substitute everything in. 988.0 hectopascals plus 1.175. And I did it again. Let me put all this below so we can fit it all on one line. So it's plus 1.175 kilograms per meter cubed times, that's the density, acceleration due to gravity, 9.81 meters per second squared, times the height of EMOS, 196 meters. And let's carry this forward, and let's go ahead and do the arithmetic. So we'll go ahead and do that. Not sure if we can just reuse. Oh, very convenient. Looks like we can reuse a calculation we did previously. So the only difference is the so-called new and improved value for density, which we determined was 1.175. So 1.175 times the acceleration due to gravity, 9.81, times the altitude at which the weather station exists, which is 196 meters, and if we do all of this, we get a number that is 2259 2259. 2259. And we know that this is a value in pascals based on the work that we did before. I'm not going to go through all the units and everything again. Hopefully that's fairly self-evident to you. And if we go ahead and speed our way through the calculation to get the second number into hectopascals, I'm going to divide by 100. That'll give me 22.59 hectopascals. And if we do the arithmetic here, so we divide by 100 to make the 22. Oh, let's see, where were we before? This number here. This number here. All right, divide this by 100. So that's our correction to account for the 196 meters above mean sea level that EMOS exists at. And then we're going to add our 988 to this. And so this is now our value in hectopascals. And we'll round it off again, so it's 1010.6. hectopascals. And that's our answer for F. So G is where we make the comparison. Let's write it here, PMSL from EMOS, if memory serves me correctly, 1011.3 hectopascal. Let me just check that. Yep, 1011.3 hectopascals, and the value that we just obtained, MSL pressure for 1F, 101.6 hectopascals. So, in fact, our so-called new and improved density resulted in a poorer comparison. And but this is what the numbers and the equation suggest, so this is what you have to follow through. Poor estimate, I suppose. This is, perhaps indicative of the fact that the atmosphere isn't a perfectly an ideal gas, and therefore the equation isn't perfect. The other thing I do want to keep in mind for you here, though, is the difference between these numbers. And probably one of the best ways to see this is by doing making a comparison on a percentage basis. So this is the value that we got. This is the value for the mean sea level equivalent pressure as measured at EMOS using our so-called new and improved density. We're going to make a percentage comparison with the actual value that EMOS reports, and I've just converted this to a percentage. So what you can see here is that this is, even though those numbers they're bigger than what we had before, we're still within, we're less than 1% away. So these values are actually quite close, and so and that is indeed what you get from making this comparison. So moving along to question G now. Question G asks you to compare and contrast. Compare and contrast the result of your calculation above 1F. That's what we just did with the EMOS reported value. And you need to report exactly what you find. So depending upon, as I mentioned before, STP 20 degrees Celsius, 1013.25 hectopascals. The values on the day that I just happened to pick data were very close to that. So the STP value for density was fairly close. We used a new and improved density based upon actually a calculation that included this temperature. It included this pressure here, the observed pressure, and the results were to within less than 1%, but perhaps slightly bigger. So when you're doing this, you are absolutely expected to report what you find based upon, and of course you have to back it up with the calculations that you did. And so H here speaks to the significance. And so in my case, because of the date that I happen to choose, I would again go back and make reference to the fact that the observations were close to ST observations. Let's start this again. I now know what I want to say. So I would say something like that the observations were made at conditions close to STP, standard temperature and pressure, and therefore the impact of the rho observed calculation was minimal. Now, that was the case for my situation. You may not have the same case. You may end up with much closer matches based upon your new and improved density estimate. And in fact, it just occurred to me that I think I've made the wrong comparison, so hang on a second here. Based on the comparisons of D and G. Right. So you should be comparing the result that you got for question 1D up here with your 1G result. So please make the comparisons that were requested. And then question I just asks you to make a comparison of the, let's see, compare and contrast your calculated density corrected based value, 1F value, with that obtained from a weather service. Okay, so that's what you need to do for 1I, is make the comparison with the value obtained from a weather service. And we pick the right screen here. Compare with a weather service. So again, that's something like Weather Network or something like that. And I think at this point we have actually completed all of question 1. We'll save question 2 for another tutorial. And so will be it, and the end of this recording.